The idea of this video is to explain the difference between a confidence interval, which is a concept from the frequentist tradition, and a credible interval, or sometimes called a compatibility interval, in the Bayesian tradition. And the way we're going to explain this difference is basically by simulating each of these intervals to actually see what they do when we generate our own data, and then we can check the result that comes out of it. Yeah, the main idea of this video is actually based on this blog post, so if you want to have more details, you're very welcome to read that blog post as well. So the idea of what we're going to do is we're going to draw a sample, x1 up till xn, from a normal distribution with an unknown mean mu and a known standard deviation sigma. Yeah, so the latter part is actually not important, but it simplifies how we generate the interval, because we don't need to estimate sigma from our sample. Yeah, so it simplifies the statistics a bit, but you could actually do this more realistically and assume that you do not know sigma either. But here we keep it simple. So we know sigma, the standard deviation of the distribution where we're drawing from. But the thing is, we want to figure out what the mu of that distribution is, so that we do not know when we do the analysis. Of course, in our case, because we simulate our own data, we actually do know what mu is. So the question is then, can we figure it out using our intervals? And what do these intervals then mean? So in both approaches, we're going to be using a 95% interval. And the way to define that as a function is actually the same for both intervals. So both for the frequentist and the Bayesian approach. So we have a data matrix X, and we have our standard deviation sigma, which we know. This is the standard deviation from the normal distribution from which we're drawing. So this data matrix X should be of a specific form. In particular, the repetition of the experiment is going to be done in the rows, and the sample that we draw, so below we're going to draw a sample of 9 observations, that's going to be in columns. Yeah, so this function interval 95, what it expects to see is a matrix X, where the rows in X form the repetitions of the experiment, and the columns in X are actually the outcome of one particular experiment. So that is the 9 draws that we get out of our distribution. Yeah, so given that X satisfies this criterion, then we can see that the sample mean is the mean of X, where we take the mean across columns. Yeah, so for each row, I'm going to get a mean. So that means that the mean is taken across columns, which is X is equal to 1. Then we can determine the standard deviation of the sample mean. And that's going to be sigma divided by the square root of n. And in our case, n is the number of columns. So when we look at the variable x and we look at its shape, then shape returns 2 numbers. The first number, which has index 0, is the number of rows. And the second one, which is index 1, is the number of columns. Yes, so the number of columns is our sample size. And here we take the square root of the sample size, so the square root of n. Yeah, so the expression that you see over here is actually sigma divided by the square root of n. And then we can construct our interval, which is going to be the sample mean that we calculated, minus 2 times the standard deviation of the sample mean. And then the other side of the interval is the mean plus 2 times the standard deviation of the sample mean. And the 2 is, of course, the fact that given that this is a normal distribution, going 2 standard deviations to the left and to the right, starting from the mean, will give me 95% of the observations. Yeah, so that's where the 2 is coming from. And we're going to do this experiment for a given mu equal to 100, and we're going to set sigma equal to 10. Yeah, so I can run this code now. So now we're first going to be looking at the frequentist confidence interval. So in this case, mu is fixed. So the parameter mu is not random, it's a fixed number. We may not know it, but it's a fixed number. And all the randomness comes from the fact that we draw data out of this distribution with a mu equal to 100. Yeah, so the different data draws gives me the randomness, for which I can then later on calculate the 95% interval. So let's define repetitions. So we're going to repeat this process 100 and then 100,000 times. The number of samples that we take is going to be equal to 9. So then my matrix X is going to be NP random normal. Yeah, so X is going to be the draws that I get from my distribution. So that means that there's going to be mu as the expectation of the distribution from which we're drawing. And there's going to be sigma as a standard deviation of that distribution. And now the important part here is the size. The size is going to be equal to the number of rows is the number of repetitions. And the number of columns is going to be n sample. And now I can calculate, intervals as interval, my function interval 95, which I call with data matrix X, and standard deviation sigma. So then we can see what this actually is. So when we call interval on this matrix, I'm going to have 100,000 different intervals, and what the function returns is this left part of the interval and the right part of the interval. Yeah, so the boundary on the left and the boundary on the right. Yeah, so that's what intervals is generating here. So now I can define my test. So when is it the case that mu lies within my interval? So the first that has to be the case then is interval 0. So this is the left boundary of my interval. So mu should be to the right of that. Oops, this is actually wrong intervals. And the second requirement is that mu should be to the left of the right boundary. So intervals, my boundary on the right. And then what I want to know is, so test is going to give me, that's a Boolean variable, so it gives me a number of trues and false, which are represented in Python by ones and zeros. So basically what we're going to do is we're going to sum test, so that will count the number of cases where mu actually lies within the interval, because it will satisfy the fact that mu is above the boundary on the left and it's below the boundary on the right. So it satisfies both these criteria. So if we want to have this as a percentage instead of an absolute number, we define it by the length of this Boolean variable test. And you can see that this is approximately 95%. Yeah, so when I follow this procedure of forming my 95% intervals based on the sample mean, what we see is that following this procedure of forming confidence intervals, it is the case that in 95% of the cases, this procedure will lead to an interval that contains mu, that contains the true parameter mu. Yeah, but the randomness here is on the interval, it's not on mu itself. Yeah, mu is, it's unknown, but it's a fixed number. There is no randomness about mu. So now we move on to the Bayesian approach. And there, the idea is actually very different. So now we're going to try to capture the idea that there is uncertainty about mu, and we know our data. Yeah, so data is fixed in the Bayesian approach. It's the data that we have. It doesn't change. It's what it is. But we are uncertain about the variable, the value of mu that actually generated that data. So in order to model this, in order to simulate this, it's actually slightly complicated. Because now we're going to have different mu's. For each mu, we're going to generate a sample. And then that sample has to be, in principle, identical to the data that we have. But we're going to allow for some slack, so it's going to be very close to the data that we have. It's not going to be identical, but it's very comparable, it's very close to the data that we actually have. Yeah, so we're going to model this as follows. So we're now going to say mu is NP random normal. Oh, actually we're not going to use normal here. We're going to say it's uniformly distributed between 80 and 120. And the size of this is repetitions by 1. Yeah, so this is just generating our mu. So we're not generating samples here, so that's why we do not have n samples here. But for our experiment, we need to generate 100,000 different values of mu. Yeah, because there's uncertainty about mu, so in our simulations, the way we capture that is generating a number of mu's. Then we're going to have our data. It's going to be NP random. That is going to be normally distributed. Normal. 100. Standard deviation sigma. And the size of this is, we're only going to do this once, yeah, because this is the data that we're going to be comparing it with everything. So this is simply generating one data set called data. So this is the data that we have. Actually, we don't need these brackets here. And I can delete this one here as well. Yeah, so this is the data set that we have. And the idea in the Bayesian approach is this data is fixed. Yeah, it's not going to vary, it's a fixed data set. So that's why we only generate this data once and not 100,000 times. The thing that we now let vary is mu itself, and that will be generated 100,000 times. So now I can calculate the interval. So this here is interval, not with an S, because there's only one interval. And that's going to be interval 95 with data and sigma. Then M is going to be the mean of our data. And Y is going to be all the different samples that we can have with mu, sigma, size equals to repetitions and sample. Yeah, so here I have all my different samples. So this is normally distributed with expectation mu, where we have different mu's in each row. Yeah, because the uncertainty is about mu with the Bayesian approach. So we have different mu's here. Sigma is known, so that's simply sigma. And the size of this is that we're going to generate these samples 100,000 times. So that's the same as above. Now we define precision, which basically means how close should the generated sample be compared to the data that we have. So it was this sample over here. And here I will work with a precision of 0.5. Yeah, so given that we're drawing from a distribution which has mu varying between 80 and 120, 0.5 is pretty small, but feel free to reduce it if you want to experiment with that to get higher precision. Now here we get to the important part in the Bayesian approach. We're going to define a mask because we're not interested in all the different samples that have been generated here. We're only going to be interested in samples where it's actually the case that the mean in the samples that we generated minus the mean in our data, yeah, so that's the one over here. In absolute value, this should be smaller than precision. Yeah, so in principle, we should have the same, our different choices of mu should lead to the same data that the data that we have. But the only relevant property of the data that we have is actually the mean of that sample. So the requirement that we introduce here is that for each row in y, I check whether the mean of y is actually pretty close to the mean of our data. If it's not, then I simply throw out this repetition that we have in y. I simply throw out this row. So now we're going to focus on the values in y where mu, where mask is true. We're going to be looking at cases where we have drawn samples from y that are close to our own data. Yeah, so now we say that the mu's that we're interested in come from the vector of mu's that we defined here, which actually satisfy the criterion in the mask that the outcome of the draw, so the sample that we draw from this mu, is very close to the sample that we actually have. And then I can formulate my test. So it should be the case that the mu that we're looking at lies to the right of the left boundary of the interval, and it lies to the left of the right boundary of my interval. Again, this is a Boolean vector, so there are zeros and ones, and I'm interested in the cases where this condition is satisfied. And I divide this by the length of this variable test. Yeah, so that's slightly complicated here because this is not simply the number of repetitions, because I've thrown away some of these y's because they generated a sample that was far away from the sample that I actually have, yeah, which was here defined in data. So let's see whether I didn't make any mistakes here if I run this. No, so I don't get an error. And again, you see that this is close to 95%. Yeah, so the credible interval, or the compatibility interval that we constructed here for the Bayesian approach, indeed, it is the case that my random variable mu lies in the interval that we construct in 95% of the cases.